Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is illustrating ARMA models with data examples. And in this lesson, I will continue the data example of modeling the Alaska moose population with the focus on forecasting. While we have data on factors influencing the population of moose in Alaska, in this lecture we only focus again on the forecasting of the moose population without knowledge of other factors to compare later with predictions obtained using also other factors. I illustrate here how to obtain predictions using the approach when we decompose the process into a trend and a process model using ARMA. Here, we'll forecast the total moose population for 4 years, not on a rolling basis, but all 4 years ahead. We set aside the data for the 4 years and fit the trend on the remaining years. That is from years 1965 to 2002, and feed the trend based on this data. We predict the trend using the predict command. To apply the predict command, we need to first define the new data for which we seek to predict future values, those being the 4 years ahead. Note that when defining the new data, we need to define it as a data frame, and we need to specify that the new data is for the predictor used in the fitted model, here being defined as X. If you will not correctly define the new data as a data frame and do not specify correctly that the predictor is the one used in the fitted model, you'll have an error message. The residual process is now defined based on this fitted trend, since we assume we have not observed yet 2003 to 2006 moose population. The ARMA model is fitted on this residual process. We use the same orders as identified initially, although we should have applied the order selection approach once more using the data from 1965 to 2002. Next, we apply the predict command, but for the ARMA fitted model. Last, we sum up the prediction of the trend and the prediction of the ARMA model to get the final prediction based on this approach. We'll next apply ARIMA modeling, which takes into account both the non-stationarity due to the trend and the ARMA jointly into one model. We'll specify only one order difference to account for the trend, and then select the orders of the AR and MA components of the ARMA using a similar approach as before. The final model is one where the ARMA polynomial order is equal to 1 and the MA polynomial order is 0, and a difference of order equal to 1. This is our output for the two tests for uncorrelated data. Similar to the previous fit on the detrended time series, the p-values of the two tests are small. However, they're not smaller than 0.05, indicating that we do not reject the null hypothesis at the significance level of 0.05. But because they're smaller than 0.1, we reject the null hypothesis at a higher significance level. We conclude that there may be some evidence to reject the null hypothesis of uncorrelated residuals. However, we need more data to conclude on the rejection of the null hypothesis. These are the residual plots from the ARIMA fit. The residual plot is patternless, similar to the residual plot from the previous approach, with lower variability in the middle, indicating potentially non-constant variance over time. Both the ACF and PACF plot indicate the plausibility of white noise. The QQ norm plot, however, has a tail on the left, indicating that the normality assumption may not hold. Generally, we perform the residual analysis to assess goodness of fit. If there are serious departures from the model assumptions, the residuals will indicate that those departures, what those departures are, and thus on how to adjust the model. Here, the departures are non-constant variance and possibly non-normality. Both could be fixed using a transformation of the white noise. We'll also learn about models for modeling non-constant variance in a different lecture. Here we continue with forecasting the total moose population using the ARIMA modeling, and compare it to the predictions based on the previous approach where we first fitted a trend and applied an ARMA model on the detrended time series. We first refit the ARMA model based on the data from 1965 to 2002, thus discarding the last 4 years. Then we use the predict command to predict the 4 years, 2003 to 2006, all at once. We'll next compare the predictions based on the first approach using trend estimation and ARMA to the second approach using a RIMA model. We first have to specify the minimum and maximum values of the y-axis through the y-min and y-max as on the slide to make sure that we plot the data and the predictions on the same scale. Then we plot a time series of the observed moose population for the last 2 years of the data, overlaying the predictions from the two approaches. Here is a comparative plot. The black line shows the observed time series for years 1987 to 2006. The red line is the prediction of the last 4 years using the first approach, and the blue line is for the second approach. While neither predictions capture the decreasing trend in the last 4 years, the first approach is much closer to the observed time series than the second approach. In fact, a RIMA simply assumes an increasing trend, capturing the trend from 2000 to 2003. This is because the ARMA part of a RIMA adds little to the prediction since it is an ARMA model of order 1, while the prediction is primarily driven by the value of the last observation of the time series. So far, I illustrated the applicability of ARMA with 3 examples. The first example was for modeling and prediction of the volume of patients in an emergency department, an application in healthcare of great relevance for hospitals. A second application was the forecasting of the stock price of IBM, a common prediction exercise for many financial investment companies. A third example was in prediction of moose population, which can be used by environmental agencies to control the population of moose. Other applications from the fields of climatology, for example, forecasting temperature, from the field to economics, for example, projecting GDP, among many others, are subject of modeling and forecasting using RIMA modeling, but also other time series models, as we'll learn in the next lectures. Overall, with the 3 examples used to illustrate RIMA modeling and forecasting, I intended to show you some of the limitations of RIMA. RIMA modeling is easy to implement, but it captures the non-stationarity in trend, assuming similarity among prior observations, and thus it can mispredict if there are large changes in the trend. On the other hand, the trend plus a RIMA estimation approach is more difficult to implement, particularly if interested in obtaining confidence bands also, but it can capture long memory trends. Prediction using a RIMA can perform well if only short time prediction periods are considered. This lesson concludes the ARMA modeling lecture with illustration of ARMA modeling with 1 example and an overview of the importance of ARMA modeling and its limitations. Thank you.